16.1 Introduction to Forecasting. When it comes to business decision, there is often much more at stake than mistakenly predicting a snow day. Poor decision due inaccurate forecasting can lead to a career being damaged and reputation being lost. Speaking of career, let's return to the original example at the start of the chapter, where you wanted to forecast new car sales for the next quarter. To do so, you will need car sales data from previous quarters, which I provide in Table 16.1. This data can also be found in the Excel file newcarsales.xlsx. The data in Table 16.1 are known as a time series because each sales data point is associated with a specific point in time. Because time series forecasting is very common in business, it is the focus of this chapter. The very first thing that any good forecaster worth his or her weight would do is to construct an XY scatter plot of the data like the one in Figure 16.1. Doing so will provide some visual insight that a table can. See Chapter 2 for instruction on how to construct such a plot. A scatter plot allows us to look at the different components of a time series, which we will discuss in the next section. The component of a time series. Any time series could contain one or more of the following types of component: trend, seasonal, cyclical, and random. A trend component is present in a time series if a general upward or downward movement can be observed in the data. For example, although the new car demand data in Figure 16.1 jump around, they appear to follow an overall upward trend over the 12-quarter time period. It seems your dealership has experienced sales growth over the last 3 years. Our data are set to contain a seasonal component if we can detect a consistent pattern that can be associated with the calendar. For example, in Figure 16.1, the second and fourth quarters of each year show a spike in new car sales, whereas the first and third quarter show a downturn. Seasonal patterns repeat themselves within a calendar year. Therefore, to observe them, data need to be collected more frequently than on an annual basis. In other words, the seasonal pattern in Figure 16.1 would not be observable if the sales data for the fourth quarter of each year were lumped together as annual sales. Businesses that are impacted by seasonality, such as tourism, need to consider this component when developing forecasting models. A cyclical component is movement in a time series that result from upward and downward swing in the US or world economy. These patterns tend to extend beyond the one-year pattern of seasonal components. For example, the demand for framing lumber was in downward cycle during 2007 to 2010 due to the weak housing market. Finally, every time series contains a random component, which consists of unpredictable movement in the data that cannot be attributed to trend, seasonal, or cyclical components. These components is often referred to as noise because it has no detectable pattern. Some of the forecasting methods discussed in this chapter will attempt to identify these components and use this information to predict future values. We will start off by learning about a class of forecasting techniques known as smoothing methods. 16.2 Smoothing Forecasting Methods. The goal of the smoothing method category is to average or smooth out the random movement in a time series because they are unpredictable. If our forecast is an average of the most recent time series value, we would expect the random component to cancel it out in the long run. That is, the upward and downward movement attributed to the component would balance out. Smoothing techniques work best with data that are fairly consistent over time. In other words, data without significant trend, seasonal, or cyclical components. The following forecasting techniques are smoothing methods: simple moving average, weighted moving average, exponential smoothing, and exponential smoothing with trend adjustment. Simple moving average or MSA forecast. In the name of this forecasting method implies we generate a simple moving average or SMA forecast by simply averaging the most recent p-values in our time series. Let's use this method and table 16.1 to forecast Brandywine Ford new car sales for the first quarter in 2014. We start by choosing value for P, the number of periods to include in our average, which is in this case is quarters. Let's set P equal to 3 for this example. We'll discuss this choice a little later, recalling that the values for the most recent 3 quarters in table 16.1 are 151, and 141 and 142. We have the following: SMA with P equal 3 quarter number 1 in 2014 equal to 151 plus 141 plus 142 divided by 3 equal to 145. Using a 3-period SMA, the sales forecast for the first quarter in 2014 is 145 cars. Now, I'm sure your boss would like to know something about the accuracy of this forecast. When Brandywine Ford sales are tallied following the first quarter of 2014, how close will your forecast be? You can answer your boss question by applying the 3-period SMA technique to the historical data shown in table 16.1. This allows you to calculate the forecasting error for each period by subtracting the historical forecast from the historical data. The mean absolute deviation, or MAD, is the average forecast error and can be found using equation 16.1, where MAD is the mean absolute deviation, AT is the actual value for the time period T, FT is the forecasted value for the time period T, AT minus FT is the forecasting error for the time period T. Absolute AT minus FT is the absolute value for the forecasting error. N is the number of forecasting error. Table 16.2 shows the calculation for our 3-period SMA forecast. We will need them to find the MAD for the car sales data. Let's break this table down one piece at a time. Because P equals 3, the first historical forecast we can calculate is for period 4, which we obtain as follows. SMA with P equal 3 and period 4 equal to 97 plus 142 plus 108 divided by 3 equal to 115.7. A common mistake some of my students make is to assign this forecast to period 3, but recall that the purpose of calculating a forecast is to predict future values with the data you already have. You can see from table 16.1 that you already have actual sales data for period 1, 2, and 3. What you are trying to predict are the sales for period 4, which you don't know. So be sure to apply this forecast to the future period, which is period 4 rather than to period 3. We call this method a moving average because we drop the oldest value and pick up the most recent value as we move down the historical data. Therefore, to determine the 3-period SMA forecast for period 5, we drop the first period, or 97, and pick up the fourth period, which is 135, in our moving average calculation, which result in the following calculation. SMA with P equal to 3, period 5 is equal to 142 plus 108 plus 135 divided by 3 equal to 128.3. The fourth column in table 16.2 shows the forecasting error, or AT minus FT, for each period. For example, we sold 135 cars in the fourth period, and our 3-period SMA forecast predicted we would sell 115.7 cars. Therefore, our forecast for this quarter was 19.3 cars too low. Similarly, our forecasting error in the 5th period is minus 0.3, meaning that our forecast was 8.3 cars too high. The last column in table 16.2 shows the absolute value for this forecasting error, or absolute value of AT minus FT, which simply remove the negative sign for any forecasting error. We use the absolute value when we arrange the forecasting error for MAD because we don't want the positive and negative error to cancel each other out. This would result in an average error that appears much lower than it should be. Think about it. If the forecasting error for 2 periods are plus 10 and minus 10, the average error is 0, which is very misleading. Using the absolute value of the error result in an average error of 10, which is more accurate. Using the data from table 16.2, we can calculate the MAD for our 3-period SMA forecast using equation 16.1. MAD is equal to 15.9. For this example, N equal to 9 because we have to average the 9 forecasting error for period 4 to 12 in table 16.2. What we have learned is that using the 3-period SMA forecast, we would expect the average forecasting error to be about 16 cars per quarter. It would be up to you and your boss to decide if this average error is acceptable for your forecast. Of course, lower forecasting error are better than larger one. I'm sure your boss would prefer your forecast to be off by a dozen cars than by 2 or 3 dozen. Figure 16.2 illustrates the smoothing effect of the SMA forecast. The blue line shows the actual data, whereas the red line displays the forecasted values. As you can see, the SMA forecast averages out or smooths the high and lows of the actual values. What happens if we choose to use a 4-period SMA forecast? This would result in a different forecast for the first quarter in 2014, which is the 13th period in our data. SMA for P equal to 4 for the period 13 is equal to 139. I'm wondering, and I hope you are too, if our 4-period SMA forecast has the potential to be more accurate in the long run than our 3-period forecast that we calculated earlier in the section. To answer this question, we need to recalculate our SMA forecast as shown in table 16.3. First, notice that our first historical forecast is now period 5 because we need the first 4 periods for the first moving average calculation. The MAD for the 4-period MSA forecast is calculated as follows. MAD equal to 89.1 divided by 8 equal to 11.1. This average error or 11.1 is less than the MAD found for the 3 SMA forecast, which is 15.9. If you had to choose between these two forecasts, the 4-period SMA forecast would be preferable because its MAD is lower. Increasing the number of periods in MSA provide more smoothing in the forecast. Figure 16.3 shows both the actual, a blue line, and the forecast values, or red line, for the 4-period SMA. Notice that the forecasts in figure 16.3 are smoother than the 3-period SMA forecast shown in figure 16.2. By including more periods in our average, the forecast will tend to move less from period to period. We can also describe this forecast as less responsive to changes in the actual data. However, increasing the number of periods in an MSA forecast may or may not lower the forecasting error. It simply depends on the historical data. Weighted moving average, or WMA. A variation of the SMA method is the weighted moving average, or WMA, which applies weights to the historical data. This allows the forecast, or you, to place more emphasis on certain historical values and less emphasis on other when calculating forecasts. Let's demonstrate this method with our car sales data from table 16.1 using a 3-period WMA with the weight equal 3, 2, and 1. This convention is to assign the highest weight to the most recent data and the lowest weight to the oldest data. The reason is that the most recent data are more relevant, so they should have more of an effect on the forecast. Think about it. Suppose you were the manager of a retail establishment and wanted to forecast next month's sales with a WMA technique. You might be inclined to feel that last month's sales volume will have bigger influence on next month's sales when compared with, say, a month from last year. WMA allows us to apply this strategy by assigning a higher weight to the most recent historical data. Because we are averaging 3 periods in this example, we need 3 weights. Therefore, the WMA forecast for quarter number 1 in 2014 or period 13 in our data is as follows. WMA with P equal to 3 period 13 is equal to 1 times 151, 2 times 141, and 3 times 142 divided by 1 plus 2 plus 3 equal to 143 cars. Notice that the denominator for this calculation is the sum of the weight. The sales value for period 12, 142, is assigned the highest weight, or 3, because it is the most recent. The sales value for period 10 is 151, is assigned the lowest weight, or 1, because it is the oldest. Also, note that these forecasts differ from the one generated with the SMA method in the previous section. Is it more accurate? The MAD calculation shows in table 16.4 provide this answer. The forecast calculation in this table for period 4 and 5 are as follows. WMA P equal to 1 period 4 is equal to 117.5, and WMA with P equal to 3 period 5 is equal to 127.2. The MAD for the 3-period WMA forecast using weight 3 to 1 is calculated as follows. MAD equal to summation of absolute value AT minus FT divided by N is equal to 15.3. The average error is slightly better than that for the 3-period SMA forecast calculated earlier, which is 15.9, but not as good as that for the 4-period SMA forecast, which is 11.1. Of course, we can always try another set of weights to see if the MAD can be lower, as well as averaging a different number of periods. The choice of weight is an arbitrary one that involves trial and error to find a set that provides an acceptable forecasting error. The moving average technique we have demonstrated in the chapter can be effective for forecasting one period ahead and require relatively simple calculation. The purpose of this technique is to remove the noise or randomness from a time series when projecting average for future time period. However, if the time series exhibits significant trend or seasonal component, this forecasting method has a tendency to lag behind the data, resulting in increased forecasting error. Exponential smoothing forecast. One of the more popular forecasting techniques is exponential smoothing, which adjusts the previous forecast with a portion of the previous period forecasting error. Equation 16.2 shows how an exponential smoothing forecast is calculated, where ft is the forecasted value for period t, at minus 1 the actual value for period t minus 1. ft minus 1 is the forecasted value for period t minus 1. Alpha, the smoothing factors for the forecast. The value of the smoothing factor alpha ranges from 0 to 1 inclusive and need to be chosen in order to calculate a forecast. When the value of alpha is close to 1, the previous period forecasting error has a large effect on the current forecast. When the smoothing factor is close to 0, the previous forecasting error has little impact on the current forecast. I will show how an exponential smoothing forecast is calculated using our car sales data with alpha equal to 0.6. More on this later. We will begin by again table 16.1, which provides us with only 12 quarters of historical data. Our first forecast will then be for period 13 equal to 132, and we will use equation 16.2 to calculate it. As you can see, in order to calculate a forecast for period 13, I need a forecast for period 12, which is I don't have. The same holds true for calculating a forecast for period 12. I need the forecast for period 10. To resolve this issue, we need a starting forecast to prime the pump and get things rolling. To do so, I'll make F1 equal to A1, the period 1 forecast equal to the period 1 actual sales. Now I can calculate my period 2 forecast using equation 16.2. So F2 is equal to 97 plus 0.6 times 97 is equal to 97. We can now calculate the period 3 forecast as follows. Ft equal to 97 plus 0.6 times 142 minus 97 equal to 124. For good measure, I will show the calculation for period 4 for you. F4 is equal to 124 plus 0.6 times 108 minus 124 equal to 114.4. Table 16.5 shows the result of applying equation 16.2 for period 1 through 12. While I am at it, I also show the MAD calculation for each period in this table to investigate the forecasting accuracy. I'm sure you saw that one coming. Notice that there is no forecasting error for period 1 in this table because we arbitrarily assign F1 equal to A1 to start the forecasting technique. The first calculated exponentially smooth forecast is period 2, which is the first forecasting error shown in table 16.5. We are now ready to calculate our forecast for period 13, first quarter for 2014 with equation 16.2. Forecast period 13 is equal to 142 cars. And finally, the MAD for our exponential smooth forecast with alpha equal to 0.6 using equation 16.1 is calculated as follows. MAD equal to summation of AT minus FT divided by N equal to 19. How does this compare with our moving average forecast from earlier in the chapter? The exponential smooth forecast has a higher MAD than both the MSA and WMA forecast for the car sales data we were given in table 16.1. However, this relationship might not hold true for other data sets. The lesson here is that none of these methods will always provide superior result, a lower MAD across all data sets. What happens if we change the value for alpha in this example? Not only will the forecast change, but the MAD will either increase or decrease as well. I went to the trouble of calculating the MAD for our car sales example for various values of alpha and graph these values in figure 16.4. You are welcome. As you can see from this figure, the MAD trend to follow a U-shaped curve across various values of A. Ideally, we would choose a value of A that would minimize the MAD, which, according to figure 16.4, is around alpha equal to 0.35. Even with this alpha, the MAD is close to 16, which is still higher than MAD from SMA and WMA. Figure 16.5 shows the actual quarter sales, or black line, as well as forecasted value using alpha equal 0.2, red line, and alpha equal to 0.8, blue line, moving average forecast. As you can see in this figure, the role of a similar to that of the number of periods included in a moving average forecast, a larger attempt to make the forecast more responsive to previous forecast error. That is, it causes the forecast to jump around from period to period. This is because more of the previous forecasting error is carried forward to the current forecast. The opposite holds true for smaller value of alpha. The red line shows little response to the changes in the actual data value. The best value for alpha, or the one with will result in lower MAD, will always depend on the data. I describe exponential smoothing to my student as a self-correcting forecasting method. If the previous forecast was lower than the actual value, or positive error, the new forecast will be higher than previous forecast. If previous forecast was higher than the actual value, or negative error, the new forecast will be lower than the previous forecast. The amount of this correction is controlled by the size of alpha. A smaller alpha results in a smaller correction, whereas alpha higher results in a larger correction. Exponential smoothing with trend adjustment forecast. The moving average and exponential smoothing method that we have learned about in this chapter have one major drawback. They do not perform well when the historical data have significant trend, seasonal or cyclical component. For example, In the presence of a consistent trend pattern, the forecast this method generate will lag behind the actual data, which will negatively affect the accuracy. However, there is one smoothing method that is the exception: exponential smoothing with trend adjustment. As its label implies, this technique will modify an exponential smoothing forecast by compensating for any trend detected in the data. The exponential smoothing with trend adjustment forecast for period T, or FIT, can be calculated using equation 16.3, 16.4, and 16.5, where FITT is the forecast including trend for period T, FT the exponential smooth forecast for period T, TT is the exponential smooth trend for period T, AT minus 1 is the actual value for period T minus 1, alpha is the smoothing factor for the forecast, beta is the smoothing factor for the trend. Notice that we have added a couple of new terms with this method. The trend adjusted forecast for interest for period T is FITT, which is found using equation 16.3. To get these values, we need both FT, the exponential smooth forecast without trend, and TT, the trend component. In addition to alpha, the smoothing factor from the previous section, we introduce beta, the smoothing factors for the trend component, which is like alpha also ranges from 0 to 1. Equation 16.4 is similar to equation 16.3 with FITT minus 1 replacing FT minus 1. Equation 16.5 calculates the trend adjustment for the current period. You can see that there are two parts to this equation. The most recent FT minus FT, or minus 12, and the cumulative trend over the entire series TT minus 12. The most recent trend is weighted by beta, and the cumulative trend is weighted by 11 minus B2. For a relatively large beta, or closer to 1, the current trend adjustment is more affected by the most recent trend. For a relatively small beta, closer to 0, the current trend adjustment is more affected by cumulative trend over the entire time series. Again, we can use the MAD to help us choose the best values of alpha and beta for our time series. Let's put this equation to work and calculate a trend-adjusted exponentially smooth forecast for new car sales using alpha equal to 0.3 and beta equal to 0.1. As with the exponential smoothing procedure from the previous section, we need to develop forecasts from the start of the time series in order to calculate a sales forecast for period 13. We assign values for period 1 as follows. For FIT1 is equal to 97. For each quarter starting with period 2 or T minus 2, T equal to 2, we perform the following 3 steps starting with equation 16.4. We then use equation 16.5 to calculate the trend component for period 2. Finally, we call on equation 16.3 to determine the trend adjusted forecast for period 2. Let's apply this 3-step once more to calculate a forecast for period 3 to help you see the pattern. FIT3 is equal to 110.5 plus 1.4 equal to 111.9. We continue with this calculation with period 4 to 12, which I've shown in table 16.6. Table 16.6 also shows the absolute error AT minus FITT for each quarter, which we will need for our MAD calculation. At this point, we haven't done any forecasting of car sales for a future quarter, but we are now ready to calculate our trend adjusted forecast for period 13, first quarter in 2014 as follows. FIT13 is equal to 145.9 plus 2.5 equal to 148.4, approximately about 148 cars. Using exponential smoothing with trend adjusted, our first quarter sales forecast is 148 cars. The MAD for this forecast is found using equation 16.1 once again equal to MAD equal to 16.6. The average forecasting error using this method to predict sales with alpha equal 0.3 and beta equal to 0.1 is 16.6 cars. In this section, we have looked at several different smoothing techniques to forecast car sales for the upcoming quarters. These methods are popular because they can be fairly effective and are relatively straightforward to use. Table 16.7 summarizes the result of each of these techniques using our sales data from table 16.1. If you were choosing a forecast from the selection in table 16.7, your best bet is to go with 4-period simple moving average forecast of 139 cars because this method has the lowest MAD. However, we cannot generalize by concluding that the simple moving average method will always outperform the other smoothing technique. Using another data set will probably lead to a different recommendation. Thank you.